Hi everyone, second video for day 3. Let's continue where we left off last time. Verify that this is true. Denote this LHS, RHS. Let's simplify RHS. So over here, again, there's more than one strategy. You can rewrite this as sine squared over cosine squared, and this is 1 over cosine squared. But you can also kind of be a little smart about it and recall that seeing tan and secant together should remind you that there is an identity relating tan squared to secant squared. So tan squared can be written as secant squared minus 1, which further, this means my RHS is secant squared theta minus 1 over secant theta minus 1. Now the numerator, I can apply difference of squares to factor this into secant theta minus 1, secant theta plus 1, secant theta minus 1, which cancels out. So I end up with 1 plus secant theta. Now LHS, if I distribute the fraction, I get 1 over cosine theta plus cosine theta over cosine theta, which becomes secant theta plus 1. So LHS equals RHS, which concludes the verification. Our next identities deal with addition of angles, subtraction of angles, and products of sine values. So here's the motivation. Suppose you know the value for sine 30 and sine 45. Is there a simple way to get sine 30 plus 45 or sine 75? So it turns out there is, and here's how we do. We consider this construction. We take AB and we rotate it to a point C, which corresponds to angle alpha, and then rotate it further to a point D, which corresponds to angle beta. Then we do some construction. We draw perpendiculars, construct these triangles. Our goal is then to find this value, sine of alpha plus beta in this triangle, which would be opposite over hypotenuse, or DE over AD. Now the first claim here, which I asked you to fill in the details, is angle HDF is alpha. Now why is that? Let's look at it. If this is alpha and this is 90, then this angle is going to be 90 degree minus alpha, because triangle, the angles add up to 90 degrees. If this is 90 minus alpha, this angle is going to be also 90 minus alpha, because these are opposite angles. Now in this triangle DFH, if this is 90 minus alpha and this is 90, then this is going to be alpha, for the same reason being that the angle in the triangle add up to 180. Okay, so that explains that part. ED is GF plus DH. Why? Well, ED is EH plus DH for sure, and EH and GF are the same because they are parallel, and this is a rectangle here. Opposite sides of rectangle are equal. Then I divide by AD. Why do I divide by AD? Well, because I'm interested in sine of alpha plus beta, and that has an AD in the denominator. So ED over AD is GF over AD plus DH over AD. Now we somehow have to relate these ratios in terms of sines and cosines of alpha and beta. So we do a little trick. Common trick in mathematics. The first one, I multiply and divide by AF. So that's just 1. I'm not changing anything. And the second one, I multiply divide by FD. Again, I don't change anything. Why do we do this weird thing? Because I chose these so that each of these ratios corresponds to a trig ratio. And I end up getting sine alpha, cosine beta, cosine alpha, sine beta. this gives us a formula for sine of alpha plus beta. So in general, we have this set of results. Sine A plus B is sine A cos B plus cosine A sine B. Sine A minus B is sine A cosine B minus cosine A sine B. Cosine A plus B is cosine A cosine B minus sine A sine B, and so on. So these are sum of angle formulas for trig ratios, and you need to know how to use them. Let's look at an example. Evaluate these without calculator. So to get a sum of 75, we look at some standard values of trig ratios that we know, cosine 30 and 35. And this is going to be cosine 30, cosine 45. Because it's a plus, for the cosine it's going to be negative. Sine 30, sine 45. So the tricky part is to see how do I express this as a sum or difference. Now here I'm going to sort of check. 1 over 12 means I want 12 in my denominator. One way to get that is if I have fractions 3 and 4, because their LCM is 12. But if I add them, I'm going to end up with 7. But I notice that if I subtract them, but I need to subtract, this comes out to 4 minus 3 is 1 over 12. So that's my rough calculation, and that works, which means I express this as pi over 3 minus pi over 4, and then I apply the formula. Let's see a verification. Once again, verification means I look at right hand side and I apply the formula for addition of tangent. This means tan A plus tan B over 1 minus tan A tan B. But tan pi over 4 is exactly 1. So this is 1 minus tan x, or sorry, 1 plus tan x over 1 minus tan x. Since LHS equals RHS, the verification is complete. Now here's a slightly different kind of problem. Write sine of cosine inverse x plus tan inverse y as an algebraic expression in x and y. Now recall, we did something like this in week 1 when we looked at how to algebraically express composition of trig functions with inverse trig functions. So we're going to do something similar here. I'm going to let cosine inverse x be u, then I get x is cosine u, and I'm going to let tan inverse y be v, then y is tan v. This means I'm trying to find, so I have two right triangles. This angle is u, adjacent over hypotenuse, and this angle is v, opposite over adjacent. So the hypotenuse is 1 plus y squared and the opposite is 1 minus x squared. Now what am I trying to find? I'm trying to find sine of cosine inverse x plus tan inverse y. But in our new form, this is sine of u plus v, which we now know is actually sine u cosine v plus cosine u sine v. But we already know what these values are because we have constructed these triangles. Sine u is root of 1 minus x squared. Cosine v is 1 over 1 plus square root of y squared. Cosine u is x, and sine v is y over square root of 1 plus y squared. So if you were to combine and write as a single fraction, the denominator is square root of 1 plus y squared, and you have square root of 1 minus x squared plus xy. So this sort of brings together a couple of concepts that we've learned this week. That's going to be the end of this video. Next video, I'm going to revisit certain graphs that we looked at in week 1 and work with it algebraically.